Audible at the back? Okay. So one of the question in the assignment was to do human activity recognition on the data that you have collected, and we had asked you to create a decision tree. So maybe the data looks something like this. You had 500 readings of accelerometer along the x direction, 500 readings of accelerometer along the y direction and the z direction. And you could have either combined them or used them directly. So some of you were asking this question that does it make sense to use decision trees on these 500 into 1500 features directly? Right. While this is supposed to be an assignment question, but I think we can discuss it now because there seemed to be some confusion. What do you think? Does it make sense to use these 1500 features directly in a decision tree to predict the activity of concern? Why or why not? Anyone? Okay, second row. Anyone? Okay, so Khush says that 1500 is a big number of features. I don't necessarily think the number of features should be an important factor here. We're missing out something else. Something which is not directly, you don't need machine learning for that. You're given these readings, right? 500, 500, 500. If you use these 1500 directly, they may not lead to a good classifier. Why? Sorry? I can't hear you. So can folks please come on time? There's a lot of disturbance because of the chairs. Yes. Can you be louder? Dependent can be? I can't hear you. You'll have to be louder. No? Try and be louder. You're saying dependent and independent features. I think that's so can you simplify that? Let me repeat the question. Why is it not useful to directly use these 1500 features? You have used them in your experiments also, right? You've got some results. Yes. You have to be louder. Okay, so there can be some features whose information gain is very low. Again, I want you to think simpler. Yes. Not all of the features might be useful. Why? They're not? I mean that is the reason, but why would some of these features not be useful? Why would these features not be useful? That's the question. The acceleration in x, y, z axis would be highly correlated, not necessarily. So it depends on the orientation of the phone or the device. You can have them highly decorrelated also. You can have the phone in a certain position in which there is no acceleration along one of the axes. So this is one of the assignment questions. You should know this. Let me repeat the question. Why is it not useful to use these 1500 features directly in your classifier? Okay, good. So let's imagine if this was some reading given to you, accelerometer reading given to you. This is for a person, let's say, walking. If this were shifted in time by 1 millisecond or 2 millisecond, is it still walking activity? Yes? It's slightly in a different phase, but it's still a walking activity, which means that the raw position, the absolute position, does not hold any significance as such. Right? So your classifier would be something like the following. If the x acceleration at time 2.3 seconds is above a certain threshold, then walking. Does that have any significance? No. But are you able to get somewhat decent results using the raw features? No? Okay, good. So if you're not able to get, then that means that you've done it correctly. So you should not be getting very high accuracy, or if you're getting very high accuracy, that could be just a matter of chance. Any questions in this? Do you want me to repeat this? So let's imagine that so for simplification, let's just use the x-axis data, x-axis accelerometer data. Let's assume this acceleration data corresponds to walking, right? So your classifier might say that if the acceleration at 2.1 seconds is greater than 4, and acceleration at 5.6 seconds is less than 2, and acceleration at 0.9 seconds is greater than 0.2, then walking. Right? But if you just shift everything in time, that is still walking. The activity still remains walking. The indices hold no such special significance here. Therefore, your model will be a spurious model in this case. Therefore, we had asked you to create some more useful features. Let's say that if I ask you to create features on the standard deviation that you observe, or the number of zero crossings that you observe, right? Or the maximum amplitude that you consider, right? Based on all of them, you can get a better sense of the activity. So they are not specifically tied to any index in the time series. Any further questions on this? Okay. So this was one of the reasons there was a question on, can you just observe the data and see if you can differ between dynamic and static activities using some very simple rules of thumb. Good. So we'll come back now to the topic we were studying in the last class, linear regression. So it started linear regression, and we said that linear regression model will be a good model if the errors that I get are small, or some functions of the errors I get on individual points are small. One such function is summation epsilon I square, where epsilon I is the residual or the error I get in predicting the ith data point. So we then wrote that y equal to x theta plus epsilon, where epsilon is a vector, x is a matrix, theta is a vector, and y is a vector. Our aim is to learn theta, where we want to say that summation epsilon I squared is minimized. We said summation epsilon I squared we can write as epsilon transpose epsilon, which we can then write as y transpose y minus 2 y transpose x theta plus theta transpose x theta. And if you want to minimize a function of theta with respect to theta, so we do the differentiation, set it to 0. We get 0 equal to minus 2 x transpose y plus 2 x transpose x theta, or x transpose y equal to x transpose x theta, or theta equal to x transpose x inverse x transpose y. We obtained this solution last time. We worked out a few examples and we saw how we are getting the correct fit. So is it enough to just differentiate a function and set it to 0 to obtain its minima, or are we missing something? So the double derivative test. So we have not done that here. That is left to you as an exercise. Can you do the double derivative test, or finding out in this case what is known as the Hessian, and check whether it's positive semi-definite? Can the people on the first row start the attendance on an A4 sheet? Okay, so now we'll be looking at a different form of linear regression. Our aim today is going to be beating neural networks with linear regression. Does that seem feasible? Can we beat neural networks with linear regression, and the data is not trivial. Does that sound possible? So neural networks are highly sophisticated models. We have not studied them, but think of them as highly sophisticated models. We want to beat them using linear regression. And we just saw a couple of minutes back, linear regression learns lines or equivalent of lines in high dimensions. Do you think it's possible to beat neural networks with linear regression? Can you be louder, please? Okay. So to understand that, let's look at this data. I have the input feature t and the output feature s, what I'm trying to learn. So I'm trying to learn s as a function of t. Do you think a linear fit would be a good fit here? To understand this, you may want to just draw this in your notebooks in a 2D plane. Can you mark these 4 entries and see if you could fit a good line through this data? No laptop policy, please. Okay. Does a linear fit look like a good fit here? No? Why? Okay. Can you notice that? So if you go from t equal to 0 to 1, you have increased the input by 1 and the output has changed by 6. If you change the t from 3 equal to t equal to 4, again the delta in t is 1, but the delta in s is 12. So can you notice that as you are increasing t, the s is growing at a rate which is quicker than linear rate, right? So thus linear regression does not make sense, or if you draw a chart, you will be very easily able to see that it's not a linear data. Now I very specifically kept these input as s as t and the output as s. So remember high school physics, where do you use the symbol t and s? Time and displacement. What is the rule that you use? What is the function that you use? S equal to ut plus half at square. Can you thus transform the data to now include an additional feature t squared? Can you do that in a notebook? So your current table is just t, input is t and the output is s, add another input feature t squared. And now see if you can fit a linear curve with inputs as t and t squared. Okay, if you add a feature of t squared, can you now see that you can fit a linear regression curve to this? What is the linear function that you learn? S equal to what plus what? 5t plus t squared. So if I add another column t squared corresponding to 2, 0, you get 0 corresponding to 1, 1 corresponding to 3, you get 9, and corresponding to 4 and 16. Can you see that your S can be written as 5 times t plus 1 into t squared? Now you could have used linear regression formula x transpose x inverse x transpose y to obtain this expression, but here you can get it directly, like it's very straightforward. So now let's look at a question. So we modified an input feature t and we added another input feature t squared and we still called it linear regression. But is the function linear in time t? No, it's clearly quadratic in t, but still is it linear regression or not? So let's look at these questions. S hat equal to theta naught plus theta 1 t, you can very clearly see it's linear. S hat equal to theta plus theta 1 into t plus theta 2 into t square, this is also linear. If you consider the input features, then it's linear in them. What about this one? Let me show you all the questions. Okay. The fourth one is a non-linear model. The remaining three are linear models. Why? Because the definition of linear regression is linearity in parameters. And the inputs after transformation, you can see it's linear in them. Right? But you need to be able to first transform the inputs and then apply this linearity. So we're doing double checks because the biometric machine is not 100% reliable at this point of time. Some people are missing. So thus we're doing both on paper and biometric machine. So this is an important consideration. Many times people get this wrong. If you modify the input, if you apply some function on the input features to generate new features, but use the following form theta naught plus theta 1 into the first feature plus theta 2 into the other feature, etc., it's still called linear regression. So the linearity is referring to the relationship between the parameters and the outcome. The outcome being S hat in this case and the parameter. So it's linear in them. Whereas in terms of the raw input feature t, it could be non-linear. Any question in this? So with this as the ground, we will be looking at CO2 data measured at a place called Mauna Loa. Does anyone know where this place Mauna Loa is? No one heard of the term of the place Mauna Loa? Okay, let me give a hint. It's an island. It's in the Western Hemisphere. It's a part of US, Hawaii. Right? So it's one of the larger, probably the largest volcanoes, active volcanoes on the planet. So Hawaii is a very offbeat kind of a location. I don't know, maybe not offbeat, but it's very, so it's not in the mainland US, and it's a beautiful island. I know about it because some computer science machine learning conferences are held there, and it's ridiculously expensive to reach there from India. So they collect CO2 data over here. This project started in 1958. So since then they have been collecting CO2 data. Why do you think it might be useful to collect CO2 data? At a global scale, why is it important to monitor CO2? Sorry? Global warming, right? So let's look at the data, and I'll not talk about global warming. I'll let the data speak for itself, whether it's happening or not. So I download this data from the NOAA website. I do some parsing, and this is the CO2 level at Mauna Loa Observatory with respect to the different years. What do you observe? The sampling in this case, in the data we have obtained, is monthly. One reading in a month. I don't know exactly the sampling process, but the data which is made available to you is monthly data, a single reading a month. So this is the data. What do you conclude from this? Is the CO2 level decreasing over time? Increasing over time. Why do you see these jitters? Does it seem to be something does it seem to have some periodicity? Why do you think that might occur? There are different seasons. I don't know the exact physics behind this, but you can see some seasonality. So why this is also important to understand seasonality is that, let me just zoom in this one. Right, because sometimes if you don't look at the long term trends, you can get confused. So let's say you are at this time, this is 1990, some particular season, and you say that you come up with a certain policy to reduce global warming, to reduce emissions, etc. And you show that after 6 months, the level has gone down. Would that be a correct thing to do? No, because if you look at the larger term trend, that is a part of the trend itself, that is a part of the seasonality behavior itself. Therefore, you will have to look at the reduction with respect to the seasonality taken into consideration. So therefore, whenever we do such studies, it's important to understand how the intervention should be taking place, and you have to understand the entire picture before it. Any other time series, so this is time series data, any other time series data where you expect to see this kind of a trend, seasonality trend? Sea level, okay. Sea level is perhaps at a daily scale because of what? Tide, high tide, low tide. Any other time series data which can exhibit this kind of a pattern? Pollution, perhaps more in winters, lesser in summers. Solar cycle, of course, yes. Sorry? Arctic ice will again show some amount of seasonality and some amount of trend. What is the trend? Right, so that's the seasonality. The Arctic ice will increase in winter, decrease in summer. But what is the long term trend? Arctic ice is decreasing. Because of that, the sea level is increasing. Where else can we see? So now think something apart from, let's say, weather related feature. Let's say you're at Amazon or Flipkart. What kind of trends would you see? Big billion days, 15th August, 26th Jan in India, or around Diwali, Holi, etc. So you see major sales and you can see an increase in the sales. So thus time series modeling is a very important concept. Today we will be looking at a very simplified version of time series modeling using linear regression. So our aim would be to predict the CO2 level at any particular month or any particular year in this time series. Right. So we'll be looking at two different variations. The first is known as forecasting. What do you understand by forecasting? When you're trying to predict something into the future. So for forecasting, I would probably say that I have data from 1958 till 2024 January. Can you predict the CO2 level for the next 10 months? Right? Given all of this historical data, let me show that problem. So if blue data is the data you use for training and you want to predict in the orange region, that is forecasting. Or the test data is into the future, you have never seen that data. But first we will look at a simpler problem, which is just, so forecasting is also known as extrapolation, because you're trying to predict beyond a certain range that you have considered. Whereas what we typically do in machine learning very often is known as interpolation. You're trying to predict values in between the ranges you have seen thus far. So let's convert this to a machine learning problem. I'll first create an X matrix and a Y array. My X is it's just the month since the starting. So I can simply just do the range of the length of the data frame. That will give me the month since the starting, because I'm not missing out on any values. And my Y is the average CO2 observed during that time. And I can then plot this data. It's important to always mention the X axis and the Y axis. I might have missed it some places, but as a matter of convention, we should always do that. It's months since the first measurement and the CO2 level. Why do you think I'm doing this months since the first measurement instead of directly using the year and the month? Sorry?
Because from the data we can see it is varying on a monthly basis.
So when it's varying on the monthly basis, I'm just trying to do this to simplify things. Rather than saying the year is 1969.3, 0.4, 0.6, I just want to simplify the setup to something which is, this was by the way time series data, so I've converted into just extracted the month from the starting. Now I'm doing another thing which is very commonly done in machine learning, known as standardization of the features or the normalization of the features. So if you notice currently the x values, they range from 0 to 720 something, and the y values are varying from 310 to 430 something. Right. Here I am calling something known as standardization routines, which after calling them will ensure that my x features are transformed to a space where the mean is 0 and the standard deviation is 1. So I want to take a range of values 0 through 720. I want to map each value from 0 through 720 to another value which is having that particular sequence has to have a mean of 0 and a variance of 1. Similarly, I do that for the y scale. So let me show this. Just one second. Let me show what I mean. So your original x was x and transformed as x norm. Okay, this also I need to flatten, I think. Okay, so original x went from 0 through 758. This is a sequence of 759 rows. You want to take this array and convert this to another array whose mean is 0 and the standard deviation is 1. So it typically works very good in practice. So now if you notice, if I am to do df dot mean, my mean of the original x is 379 and my mean of the transform variable is 0. And if I do the same on standard deviation, the standard deviation in the raw features x is 219 and in the transformed is almost 1, like to some approximation. So there was some question.
Yes, sir. So, my question is, we also need to include for the test data set in that, right?
Yes.
We don't know the range of the test data set. We might know the x, we don't even know the x values or the y values. So, how will we account for them in this?
Okay. So Deep asks a good question, that do we include the test data in this, and let's say if the test data is very different from trained data, how do we do the normalization? So first let's assume that we do the normalization over a broad range of values. At least we know the domain of values, we can broadly agree on that. But even if you don't know, so let's say you were to give a new value which does not exist in this. So Deep's question is, let's say if I have to predict for some x test equal to numpy dot array of, so we have seen till 758. So let's say we give 800 and I do s1 dot transform, I still get a reasonable value. It's not too huge. So thus far my values from minus 1.7 to 1.7. If I give something outside the range, I'll still get a reasonable value. Okay, why do we need to do this, or what is the benefit of doing this kind of normalization? Okay, so let's not talk about out of domain. Let's think something simpler.
When we take features like x cube or x raised to 4 divided overflow.
Okay. So question says an interesting answer to this is to avoid overflow when you are looking at higher order features, like we did s equal to ut plus half et square. If we were to do t squared on values like 1960 or let's say 758, that becomes a huge number, right? Correspondingly, the coefficients that you learn will become very, very small. So there you may have some overflow as well as underflow errors. Right? The other reason is that you typically want to bring all the features to a common kind of a domain, which makes the learning quicker. So we'll see this learning aspect when we study gradient descent, one of the specific algorithms which we use. But for now, let's just use this as a matter of convention, as a matter of good practice. We should normalize our input features as well as our output ranges. But the important caveat is that we'll have to denormalize or we'll have to do the inverse transform, because the pollution value is, or our input value is not minus 1.729, it's 1959. But you have to transform it back when you may have to make the plots or when you have to interpret the results. So one mistake I've seen people make is, let me first show on the y-axis. So I did this transformation on the, I used a transformer S, not the transformer you'll study in let's say deep learning. I use this transformation function S1 to standardize the feature X, and I use S2 to standardize the feature Y. After doing this, we can again see that Y norm has a mean of almost 0 and a standard deviation of 1, which is what we expected. Now sometimes people make this mistakes. They train on X normalized, Y normalized. They use X test, which has been normalized, to predict something, and then they compute the error with respect to the true Y values. The true Y values are in the range of 300s, but now your model will predict something close to 0 or minus 1 and 1, something like that. So then if you compute the error between a number between minus 1 and 320, you will get huge errors. So you made a mistake, you have not done the inverse transform. I can now plot the normalized X and the normalized Y. Importantly, I again try to write normalized in both of them so that you are fully sure that what you are doing, because CO2 levels are never going to be negative, but the normalized one in this case can be. Now we look at the first task, which I said interpolation. So I'll do a random train test split with 70% train and 30% test. I could have used sklearn's routine, but I just did it myself here. So this is how the train test data might look like. The train points are shown in blue, which are much more. The test points are just because of the bigger circles, they look more in number. I will fit a vanilla linear regression to it. The important thing in this is, so this model when I will call will be a linear regression model from sklearn. So model equal to linear regression. This X normalized I'll give for the train set. I'll give the Y normalized for the train set, because I have to fit linear regression dot fit normalized inputs, normalized outputs. I fit that. I predict on the train set using the normalized input for the train set, and I predict on the test set for the normalized input for the test set. Now, what do you expect the range of y hat test to be? 300s or minus 1 to 1? Minus 1 to 1. So therefore, we should not be using y hat test directly to compute our metrics. What do we need to do? So while we were normalizing, we went from x to transformed. When we want to do the inverse transform, we'll go from transform to x. Right? So therefore, the transformation that we have done is an invertible function. Not all functions are invertible. We have chosen a specific simple transformation which is invertible. So we call, let me show that first. So I have this data frame. If I now do a normalized, so let's say renormalized. So I call this inverse transform method with the transformed values. And now if I look at df, can you see that I've been able to recover the values exactly? Right? So this is the exact procedure we'll do. Am I audible at the back? I wonder if the battery has died. Yes. Am I audible? Good. So therefore, I think it's important to do such practice before you go on to training the direct models. You take inputs, you transform, and then you confirm that after retransformation you get the same variables back. And then I can compute the errors on both the train and test, and then for some visualization purposes I'm doing something else. You don't need to bother about all those things for now. Okay, what do you think about the fit? The fit is a bad one. Why do you conclude that?
Firstly, does not follow the trend, and if we had something like the mean average, what's the absolute error to measure this, we will get a higher value, we will get a lower.
So we get high mean squared errors on the train as well as on the test. Like we'll have to say that relative to something, but here we can clearly see that the model is exhibiting some amount of bias. It exhibits some amount of errors for low time, and for when the time is close to 2024, which is today, it is under predicting. So it's over predicting for some times, it under predicting for some times, and the errors seem to be huge. And broadly, if we see, the trend does not look exactly linear. It seems to have a certain slope, right? Does it look more like a slightly quadratic term, right? So should that be alarming us? Why? What is the implication of quadratic growth? So it's the rate of increase of CO2 is very high now. It's not a linear increase, it's a quadratic increase. We'll see if that's the case or not. But first, let's see if a neural network can do better on this task. So I learn a multi-layer perceptron, which is just a vanilla linear neural network. And do you think it does a far better job? Right? So now our goal would be, can we beat this multi-layer perceptron, get comparable using just linear regression? This multi-layer perceptron neural network requires a lot of parameters, can be expensive, and we'll see a certain reasons why it may not be the ideal case, especially for different kinds of problems. So we, in the displacement question, we created a new feature t squared. Right? So we'll have to do the same thing here. Instead of just having features x, I will now create features x squared, x cubed, x till power d. Right? So I'll create all of those features. The code is pretty simple. I first just copy the input feature that I've given, x. Then I create x squared, x cubed till degree d. And in this case, I'm doing normalization, but you can also try without that, given that our input is already normalized. Should not be a huge difference. So I wanted to show then this specific thing. So let's say our original input is some x, right? So our input is x. Then I'm showing you different functions which correspond to that domain. in this region. So this is x squared and then x cube. Does the function look correct? What is wrong here? So would you expect x squared to be lowest at x equal to 20? What is wrong here? Sorry?
Why x square is negative?
Why can x square be negative? So firstly, you have done a standardization because of which it can be negative also. The other thing, so which should have been probably done is create xs equal to numpy.linspace poly features on x's and plot x's and y's. Now does it make sense? Now it's on the -5 to 5 range. Previously it was plotted with respect to the number of samples. But anyway, so this is what we want to do. We want to create these different featureizations, these polynomials, and somehow we want to combine them in order to learn any new function. This will become more clear. So let's go here. So what are the different functions which you can create by combining this function? So let's call this line also as a function. The new function that you can create is just weighted combinations of the older functions. What kind of different functions can you get if you just use this input function? You'll always get lines. If you were to instead have now two input functions, you can have a constant function theta naught plus theta 1 into this blue plus theta 2 into this orange function. Now for different values of theta naught, theta 1, theta 2, can you get very different kinds of overall function combinations? So if you keep increasing the degree, can you see that the different combinations can lead to arbitrarily complex functions that you can learn? So that is what polynomial regression will do. You create these higher order polynomial features which you will then input into the linear regression modules. So now I create this degree 4 features. Everything else is the same. I still just pass in the linear regression object and I just call the same function as before. Can you see that the fit is now fairly good? So now using linear regression, you have got very close to what neural network was giving you. The importance difference being that in linear regression, now you are feeding in higher order polynomials. Okay. Why do you think higher order polynomials work? Sorry, I didn't hear. So I've shown you something works. Why do you think higher order polynomials make sense?
So using that, we might the model might be able to expand or like move to different points on Mars.
Okay, good. So if you remember the initial lectures, we discussed there are two problems which machine learning models face. One is high bias, the other is high variance. So if we look at the initial model fit on this data, linear regression model, what problem does it exhibit? High bias, high variance? High bias. What does high bias mean? That the model is not complex enough, it does not have enough representation capabilities, it is not very expressive. So you want to make the model more complex. One of the ways to make the model more complex is to give it more degrees of freedom. In this specific case, the more degrees of freedom we can give is by looking at higher order polynomials. By combining higher order polynomials, you can get various different kinds of now functions which can be possible now. So therefore, by increasing the degree, you are hoping that the bias will decrease. You should be able to do a better job by combining more features. So do you think if you keep on increasing the degree of a polynomial, will the train RMSE keep on reducing? Should the train error keep on reducing as you increase the degree of the polynomials? Yes? No? How many think yes? Okay, why do you think yes?
Basically doing some sort of Taylor series. Like if you have a lot of, if you have some limited amount of data and then you just increase the degree to whatever that you want. Basically doing a Taylor series, if you increase the degree to infinity, but basically.
Good. So he's pointed out that there is some relation between this and Taylor series, but does Taylor series work on higher order polynomials, or does it look at higher order gradients? It looks at higher order gradients, right? But there is some similarity. So you should study this up in your own time. But broadly you can see that you'll be able to fit better functions if you have more expressivity. Right? Now think of it in this way. Let's assume that your data is quadratic in nature. It's quadratic in x. If you have a x cube term, should the coefficient of that term just be 0? Right? So therefore adding more terms should not harm your training error. It should only improve your training error. It should only reduce the training error. That's one way to think about it. There are some corner cases in which such intuition starts failing, but for the simple cases we'll just agree with this. So here we see that a degree 4 curve does fairly well. Degree 2 curve was also doing well, but if you notice the train on MSE was 5 and the test was 6.68. If I did degree 3, the train has reduced, the test has slightly reduced. If I did degree 6, the train is reducing, the test is reducing, so on and so forth. So we'll be now varying the degrees and observing the train and test RMSE to figure out an optimum degree D which we can use. So thus D is serving as what? As a hyperparameter which you are trying to tune. I wanted to show something else also now. So if I had a model of, if I had a degree 4 model, the intercept that I get is minus 0.01 and I get 4 coefficients corresponding to x, x square, x cube, x4 like terms. Right. Now what I want to show is that this particular function that you have obtained, what is the form of it? It is the intercept plus theta 1 which is 0.97 into x plus 0.09 into x squared plus 0.019 into x cube plus 0.02 into x4, right. So each of them are being added up to make the overall function. So I wanted to show you the different components. One is a constant line with respect to the input, it's a constant line minus 0.01. The second one is this line minus 0.97x. The next one is this function 0.09 x square and so on. So I have these different functions which if I plot them, you can see that there is a degree 0 term which is just this line. There is a degree 1 term. So these are the learned functions which we will be adding up to obtain our true data, to obtain our estimated function. There is a degree 2 1, there is a degree 3 and there is a degree 4 curve that you have learned. So I wanted to show this. If you consider a single term, an order 1 term for this function, you obtain minus 0.01x plus 0.98 into x. You can see that the approximation is fairly bad. If you were to increase this to 2, you can see that the approximation has become slightly better. It's still exhibiting some bias here, for example. We will now increase this and see if the bias reduces. Can you see the bias is slightly reduced, not significantly.
But it has increased at the bottom.
It has increased at the bottom. Okay, but perhaps somewhere else it has readjusted, because on the training data, you are expected to get better if you increase the degree. So therefore, you can do this as an exercise. You can keep varying the degree that you allow it to fit, and you can see iteratively how the function keeps getting better. So now let's see. So if you see the bias over here, and it reduces when you go from 3 to 4. Right? So therefore, you can think of what we are doing in multiple ways. You can think of it as we are doing this weighted combinations of the different functions. Different functions being different order polynomials here. And then we can just run this function across varying degrees, and we can see the train and the test error, which is what we said. We can look at the bias variance trade-off or do the hyperparameter optimization.
Is the y-axis correct in the above?
The y-axis should be, I think it's correct, because no. So I am plotting after inverse transforming, so that we get a sense of the values that we are predicting. Okay, what do you observe from this plot? These are the train and the test errors. What do you conclude?
That after a particular depth, the increase that we get, by increasing the depth, is not significant enough for.
So in this case, the depth is not the depth, is the degree. We can broadly see that as we increase the degree, the train error will go down. The test error also goes down till a point, and after that it increases. So that is probably more visible here. We look at the mean squared errors. Initially, for low degrees, the mean squared error is very high. We saw the errors were something around 20. As we keep increasing the degree, you see that the train error keeps going down, which is as expected because the model is becoming more flexible to fit the underlying data well. But the test error reduces to a certain point, and after that it starts increasing. Right? So then what do we understand by this region? High variance or overfitting. Right? So therefore, throughout the course we will be looking at the bias variance trade-off with respect to the different models that we see and the different hyperparameters and the parameters that they give us. But the important thing here is that we have almost matched the performance of neural networks, but with the linear regression model. So therefore, we should not be discarding linear regression as a useless model, especially if you are able to bring in some amount of domain insights and you can create the features in a way. Okay, the next topic is a slightly difficult one. So if you are very considerate on your friends, you may want to just wake them up. Slightly complicated compared to the previous ones. Yes.
Not just for linear regression that we are studying right now, but as we observed here, even neural networks could not predict the periodic change in seasonal change that was happening in data, whereas from the data it was, but the entire data was, but it was significant.
Yeah.
Is that a limitation of ML as a whole, that it will never be able to predict such periodic trends, or with increasing complexity that would be possible?
Okay. So Deep is asking a very good question. From the domain expertise, we knew that the function is periodic. The ground truth data is indeed periodic, but we saw that even the MLP that we looked at wasn't able to do. One, the MLP which I showed you was a very simple one. If I worked hard enough on it, I would be able to do somewhat better, but in general, periodicity is not very trivial to capture. But I can show you another function, another machine learning model.
So we can add a sample.
Whites were sampled for testing and training such that we could not see the periodicity completely in the training.
I think we had enough data available to get the periodicity. It's just that the model did not have the specifics to learn that. For some reason this is not running. Let me show you the version which it ran. Let's see. Can you see that this function has been learned in a way that it's able to capture the periodicity? So this particular method is known as Gaussian process regression. I will not go into the details of this, but importantly, if you notice, it has got something known as some specific method, some specific hyperparameter or kernel in this case, which allows it to model for the periodicity present in the data. So if you can do that, then you should be able to do. Okay, so we have looked at one particular kind of basis. So these things are known as basis functions, by the way. The basis function that we have currently looked at is known as polynomial basis. So we've expanded the input to a high dimensional space, right? Our original input was in a 1D space. We have now projected it into some D dimensional space, in which if we do linear regression, we will be able to get a fairly good fit. Now we will be looking at something known as a Gaussian basis. How many of us know the Gaussian distribution? Okay, the others who don't know, I am sure they know, but they are tired. Okay. Let me first show what I can. So now again for a simple, so now can you see that I am showing you three different bases, three different Gaussian distributions, right? Now what I am saying is that any function that I want to get, I can get by combining these three different functions, right? So if I wanted to get a function something like this, I will say some value of this plus some value of this plus some coefficient multiplied by this. This is similar to the way we had derived the polynomial basis. Right. So in this particular case, we had one function or one input feature x, the other input feature is x squared, the other is x cube, and so on and so forth. Now by combining all of them, I can get arbitrarily complex shapes I can model, arbitrarily complex data I can model. But in this case, I am using a Gaussian distribution to do this modeling. First, let me show certain variations of this, and then I will come back to what exactly we are doing. So D is the number of Gaussian distributions that I am learning, and standard deviation is the standard deviation of the different Gaussians that I am learning. So now what I am saying is that I can create, I'll give certain weights to this feature, to this feature, to this feature, to this feature, to this feature. I have 5 extra features that I have created. So basically theta naught plus theta 1x plus theta 2 into this plus theta 3 into orange plus theta 4 into this, theta 5 into this, theta 6 into this, right? And using this basis function, I can learn fairly complex data patterns. If I increase the standard deviation, what do you observe? The functions will get flatter, right? If I decrease the standard deviation, the functions will get very peaky, right? So the very peaky functions are looking at a very small local region, whereas very high degree of standard deviation is looking at a very broad region, and you're trying to combine these in some way. We can look at different degrees, different number of Gaussian functions which I learn. So if you think of this as just an extension of what you had done in the polynomial basis, this should be fairly simple. But if you don't think about that, this interpretation might be slightly harder. So what we have to do to create this is, I have to firstly know the number of polynomials, the number of Gaussian bases that I want to create, Gaussian functions. I evenly divide my input space in this case into 3 points, right. So, this becomes my first point, this becomes my second point, this becomes my third point. On each of those values, I center a Gaussian with a certain standard deviation which I have provided. So, that is all this function is doing. I create the means, mean vectors. In this case, we have a mean vector corresponding to 3 values, and I create a Gaussian around each of them. The Gaussian has a specific property that first it's symmetrical and the values in nearby regions are similar. So, therefore, the reason why we are doing this is to learn some functions, some basis functions, which if we combine, we will be able to learn some smooth patterns. And by the virtue of this, we will be able to learn some locally smooth patterns, because Gaussian gives you it's a locally centered Gaussian that you have. I will just show the outcome of this now. So, in this case, I am using certain degree polynomials with a certain certain degrees of Gaussian basis, certain number of Gaussian basis with a certain standard deviation, and you can again see that we are doing at least better than linear. If we fine tune this enough, we should be able to get comparable performance to polynomial regression. See, so for 4, 5, 6, we see that the train and test error is quite low. So, let us in fact try and run this for 4, 5 and 6. Now, the fit is quite good. Right. Now, what you might be finding a little hard is to understand that this particular green function that you see is some theta naught, some constant, plus some theta 1 into x, some line, plus some theta 2 into one Gaussian, plus theta 2 into some other Gaussian centered at some other point. So, if you visualize it that way, you should be able to create a visualization which is similar to what I had created here. Okay, sorry, something has changed here. So, now there are two hyperparameters which we had in the Gaussian basis. One was the number of Gaussian bases that Gaussians that we put. The second was the standard deviation. Now, whenever you have such kind of hyperparameters, it's a good question for the bias variance trade-off. If I increase the sigma, this sigma, the standard deviation, if I increase the sigma, do you expect the functions to exhibit higher bias or higher variance? So, by increasing sigma, can you notice that the functions are becoming very, very smoothish? They are looking at very long term trends. Whereas, if sigma is very low, they are looking at very local trends. What is more closer to overfitting? Local trends, when you are trying to capture some very local specific aspects of the training data, it may not generalize well. Whereas, on the other extreme, you are looking at some very, very simple functions almost like lines. So, you will exhibit higher bias. We might expect to see something like this. So, therefore, I am varying my standard deviation now in 0.1, 0.5, 1, 2, 5, 10. Typically, for such things, it may not always be linear scale. You may have to look into the log scale. In this case, I am almost looking at a log scale. Okay, what do you observe here? We can notice that again there is some bias variance trade off, and you can see that for one particular value of sigma, the loss keeps going reducing. The training loss you can always keep on reducing by making it more complex, but the test loss error will keep increasing will increase after a certain point. So, again there is some trade off. You have to choose some particular point in between which matches overfitting, underfitting. Okay, how many of us have heard of GPT, chat GPT, attention transformers? How many have just heard? I don't. Okay, so these particular models, they end up using something known as positional encoding. Has anyone heard of this term, positional encoding? So without going into all of the details, positional encoding is in some sense another basis expansion. We have looked at the polynomial basis, we have looked at the Gaussian basis, now we are looking at something known as the Fourier basis, which is to just say that our new features are of the type cosine of 2 pi b into x bx and sine of 2 pi bx. Right? For certain values of b, you create these new features cos something into x and sine something into x. Now let's go back to the original data. Do you think a cosine or a sine curve might have made a little bit of sense here? Why? The data is inherently periodic, but the periodicity is at a very long time scale. So therefore, the frequency should be a very small number or a large value, large number. So frequency large means the signal is very frequently changing. Frequency less means the signal is very slowly changing. It exhibits a periodicity at a very large interval. So therefore, some amount of periodicity you can capture via cosine and sines transformation of the input variables. So these particular things which I am showing, they also get used, as I mentioned, in something known as positional encoding, which gets used in attention mechanism. I can show you that this has been picked up from there. Right? Something known as positional encoding, which provides some additional context or some additional input features for time series like data. We don't need the specifics of that, but you can see that it's fairly similar to what I've shown here. Right. So this value b, I'll be sampling from a normal distribution with mean 0 and variance sigma squared. Right. Essentially think of it as I have now created these depending on the different values of randomly sampled values from the normal distribution 0 sigma squared. I can create these different featureizations. Okay. Again, if this looks complicated, let's go back and see what we did here. Here we're creating different order polynomial terms, x, x square, x cube, right. So three features, you have x, x square, x cube. Here in Gaussian basis, we have divided the input space into 3 points. Each point is serving as the mean of a Gaussian distribution, and you put a Gaussian distribution with a standard deviation around that. This gives you 3 different functions which you will use further, similar to x, x square, x cube, similar in principle. Here you have created now in random Fourier features, we have created these different combinations. So let's just do num features as 1. So I've created a sine and a cosine as an additional feature, right. So sine of my input x, sine 2 pi into something into x, and cos of something into x. These are 2 additional features that I've created. I can vary gamma if I am not doing it here. I can vary gamma and show you. So if gamma is 0.1, why do you think this occurs? If gamma is a very small number, why do I see some lines? So gamma, so this is what I meant by, I think, b. So if, right, so if gamma is a very small value, so this should actually have been sigma, I think, sorry. This gamma should be sigma, this is not gamma. I just right. If sigma is a very small value, if you draw from a normal distribution with a very small standard deviation centered at 0, the values that you'll get is very small itself, close to 0, right. So in this case, the value which I get is 0.049. Now sine of a very small frequency and cosine of a very small frequency are very slowly changing signals. Right? So they will exhibit periodicity over a long trend, over a long time period, and this is what is happening. If I increase this to 1, I get a value of 0.49. So, this is sine of 2 pi into 4, sine 2 pi into 0.49 into x and cos of 2 pi into 0.49 into x. So, therefore, you can see a higher order speed of the function or higher frequency. If this was 5, the value which I get is 2.5, and you can see I get this periodic kind of signal, but I can increase the number of features that I create. So, number of features means that I do more random samples from this normal distribution. So, many of you do not yet understand the normal distribution, how to sample from it, you do not need to worry. For now, you can just use this as some routine which I have given to you. Right. So, you can now see that you have created various possible functions of varying frequencies. And why do we need to create both sine and cosine? Why not just create sine?
Because sine essentially models odd functions and cosine essentially models the even functions. So
Okay, good. You can think in terms of even or odd functions or something simpler. Okay, you can create, so the important term I was hoping was for there is a phase difference between them, right? So, sine would always give you a 0 at input 0, cosine will give you a 1. And if you had a non-zero value at x equal to 0, using just combinations of sine, you will not be able to learn that. Therefore, you want to have a phase difference entity also. So, we can also use scikit-learn's inbuilt functions to create these features. The details I am skipping here, but for those who are interested, this is something known as a kernel approximation, and what you are getting is a specific type of kernel approximation which is known as RBF sampling. I will skip all the details. So, now I have created various of these sines and cosines as features. So, now my input features is x and then sine of something and cos of something with different values of the b multiplier, and now also you can see that the test RMS is quite low. Right. Okay. So, again now you have a sigma parameter. You had this sigma parameter over here when you are trying to create these additional features. So, you will again have a bias variance trade off with respect to sigma. What do you think that is? High value of sigma means what? High value of sigma will give you what? So, it is more variance in the normal distribution, because of which the b value that you will get, which is sampled from this distribution, would also likely be large, which means that the functions that you are getting are likely smoother, right? They have a larger periodicity, but if the sigma is very small, you likely get some local functions, some which change very rapidly, higher frequencies. So, we expect to see this kind of a behavior. Let us see if that occurs or not. So, importantly, you can notice that this sigma is shown on the x axis and the y axis I am showing the errors. Again, you see that the train error is becoming better for some reason, but the test error exhibits a pattern after which it starts becoming worse. So, we have again identified a point beyond which you should not be tweaking your model. It goes into the overfitting region. The next task which we will do in the next class would be to see how we can extrapolate this data or forecast this, but we will not be using something known as something complicated like LSTM or CNNs. We would again be just using linear regression, and we would see if we can get fairly good performance or not. So, today's class I would say that you need to go through it slowly because there are some nuanced concepts, some concepts which require a bit of time. So please do give it that proper time. It's not as trivial as, let's say, just x transpose x inverse times x transpose y. You have an assignment Viva today evening. All of you should have signed up. If not, please do that right away.